today we will be studying, or I will be showing you the 4 velocity vector. V right here is an index. You set V to be a value, like I say, V is 1. V is the velocity along the x. If this is u1, that is equal to the velocity along the x-axis. If u is 2, that is equal to the velocity along the y-axis. V3 is equal to the velocity along the z-axis. U0 is actually the velocity through time, which that changes while these change as well. So, we're not going to get too into this time velocity here, so let's just act like that doesn't exist. So let's just say that a object with momentum, right here, this object's moving with a momentum of 5, let's say, units of momentum, kilogram meters per second, and its mass is 1 kilogram. And then it collides with this object that has a half of a kilogram. And then this thing's resulting momentum after the collision is just 0. So it gives all of its momentum to this thing. We can calculate using, basically, we can calculate, if this thing just has no momentum, then it gains all the momentum from this thing. We'll set this, say that's 5 kilograms meters per second squared. Or 5 kilograms meters per second. And if the momentum is equal to mass times velocity. But let's just put one thing into account. In the 4 velocity vector, this thing is only moving along the x-axis. And this thing is also only doing that too. And considering we are basically just saying it's the 3 velocity vector, it's no longer the 4 velocity vector because we're not going into the time. I don't even know why I called it the 4 velocity vector, but I was just saying that that's usually what you'd use, but we're not getting into that yet. But that's but like this is only assuming it's the velocity along the x-axis. So then we divide by the mass of this thing, which is 0.5. That takes that away. And then we just get the velocity. And this is how the units work. You just get rid of the kilogram part. And that gives you 10 meters per second. So this thing's velocity goes from 0 meters per second to 10 after collision, which is a very high velocity, actually. Not very high, but it's pretty high compared to this object who's only going at 5 meters per second. But this just shows the magnitude at which momentum has on like objects. So let's go on to a different paper and do some more stuff like this. So we have an object moving along the x and the y axis. That's actually how you write the velocity along the x-axis. It's the change in the x position over the change, like the time, or let's put it as over time. Just try to be a little bit more easy, but it's over basically the change in time. And then we have it over that same thing. So we just have like delta y over delta time. So it has a velocity for x and a velocity for y. It's right here. Now its mass is equal to 2 kilograms. This is also including lots of momentum problems. Let's say that its velocity, or that its change in its x, like its x, like right when it hits this object, this change in x part right here is 5 meters. And the change in time, or this time, is 2 seconds. That's equal to 2.5 meters per second along the x-axis. And we can actually put this into a vector. So let's say 2.5 meters per second on the x-axis. This is how you actually write a vector. You have like a little bracket, like a little parentheses, and then you have comma, and then you have another component. Or you can use like vertical vectors, but we're not going to do that. So let's say that delta y is equal to, let's say, 6 meters. And then that is the same time. So then that would be 6 over 2, which is equal to 3. And the same math. Then we need to know its momentum for each axis. The momentum for x-axis is equal to the mass times the velocity for the x-axis. Now the x-axis velocity is 2.5. And multiplying that by 2, we get that's 5 kilograms meters per second. Now that for y is 6. So then, what if we have another object right here? This object's is moving on 0 for both axes. And then it has a mass of 1 kilogram. And then this thing transfers half of the momentum on each axis to this thing after collision. So let's divide by 2 on both this momentum, and that's basically going to give us back this vector. By the way, you can always pause the video and solve it yourself if you really want to. But I'm giving you the good formulas on how to solve it if you get like problems like these. That's basically it. And then you divide that, the mass of this, to get the velocity as you dictate by this formula. So then the velocity after collision is the same as the velocity of this object before collision. Because the masses, if you have like a half, then the masses just kind of reduce into like the same sort of, you know. Now, if you're not too familiar with these formulas I just showed you, I will basically punch them into your head. Metaphorically speaking. I would not do that in real life. What? Actually. Just to let you know, YouTube, I did not actually mean that. That was just a joke. Okay? Just to let you know that. That's metaphorical. Okay? Metaphorical. I would not punch them in your head, okay? I punch them in your head, I mean, if you listen, you get them in your brain. Not actually punch them in your head. Just to put that out there. So let's say that momentum for x is equal to mass times velocity for x. That's basically because you have the formula of mass times velocity, and you just plug in values for that. But this has the velocity for the x-axis, basically just how x changes with time, and then y-axis and z-axis. How y-axis changes in time times mass. How z-axis changes with time times mass. That's basically it. But let's go over it one more time. It's basically just this term right here is just how x changes with time. The x-axis changes with time times its mass. This term right here is just how the y-axis changes with time times mass, and it's the same thing for the z-axis. So hopefully you enjoyed. Just put that out there because YouTube's a little bit, if you say a little bit something like that, they'll get on you. I did not mean the last thing I said when I said I'd punch it in your head, okay? I did not mean that. I did not mean when I said I was going to punch this info in your brain, okay? Just to let you know that. Goodbye, peoples. Or goodbye, peoples. Peoples.